Good morning, everybody. I'm so excited to be here to talk to this wonderful audience about a topic that I think a lot about, spend a lot of time reflecting on, actively building in this space as well. And so the topic obviously is beyond the hype, designing human-agent collaboration for decisions that matter. And I want to start this conversation with a thought experiment. So stay with me, because I'm going to come back to this at the end of the talk. And by then, I'm hoping you'll think about it a little bit different than how you're thinking about it right now. Imagine you are an operations lead at a hospital during a surge. You have 10 ICU beds, 40 patients who may need them, 1 hour. Every hour, the decisions that you have to make change, right? The situations evolve every hour. Your staffing is constrained. There's not much transportation available to sort of dispatch patients in different locations. However, you have a new AI agentic system. It ingests the vitals, it looks at the labs, it looks at all the clinical data, it looks at what the risk score is for every patient. It proposes a bed allocation, proposes a transfer mechanism if needed. It's fast, it's consistent, it's accurate on every historical data that the hospital ever had. It saves your team tons of hours every shift. So here's the question I want you to sit with. What would you need to see before you dispatch this agent into live data, into live production? It's not about model accuracy, because that's historical, right? What sort of mechanisms do you need to see or do you need to set in place for this to be a safe exercise to be held in production? And then there's a harder question, right? What if this model was wrong only 1% of time? That's pretty good, right? Just 1% of time, very, very accurate. But these mistakes are silent. They show up probably a couple of days later. 1% is very, very reassuring, but in busy hospital where you're making hundreds of decisions over thousands of patients, where this result is slow trickling after multiple days, the issue with that 1% is you can never correlate the harm that has happened with the source, because the feedback loop is so long. And that is the reality of decisions that matter, right? It's not about neat errors or cute matrices that we draw when we evaluate our toy models. It is really about outcomes. And this is the central tension I want to talk about today. Just to give you numbers real quick, right? 2024, 0% of obviously enterprise work decisions were made autonomously with AI. We believe that about 15% of work decisions at enterprise level will be made with AI by 2028. 15%, not too bad. Think about it, 15% of every work decision. What this means is procurement decisions, hiring decisions, resource allocation decisions, content moderation at scale, how patients get routed, 15% of everything to be driven by AI. We also have another wonderful number, which is this market is massive, right? We do believe that by 2030, this is going to size up to about 47 billion. That's still on the lower side of the numbers that we see right now. Here's another fun one. When execs were interviewed to describe agentic AI, 76% of them called it a coworker and not a tool. Fun. But here's the other side of this story, right? 40% of agentic AI projects are predicted to be canceled before production by 2027, which is like pretty soon. And this is a very interesting graphic here. There's a lot of enormous ambition. There's a lot of investment that is being made. But there's also a lot of skepticism about what can be really deployed in production. The specific gap is because we're asking the wrong questions more often. It's really not about capability, right? It's a lot about reliability. Models are incredibly capable right now. And so the question is not about can we build this agent? Of course we can build a lot of things right now. The real question is, should we be building this agent? for this type of autonomy, for this decision type, for this user group, with these stakes in our hands, right? And that question really changes the framing of how we think about building agentic systems for difficult decisions to be made. Fundamentally, it's also an architectural shift on how we evaluate, right? With traditional machine learning models, a unit of failure is a wrong prediction. You are able to trace back on, oh, this particular data source probably did not align with what we've seen in the past. It's a wrong prediction. But with agentic systems, where you have an orchestrator with multiple agents acting in different directions to execute different outcomes, it's pretty much a wrong trajectory, which is the unit of failure. And this is very different because we don't have robust systems to measure a wrong trajectory. Before we even jump into the design frameworks for high-stake decision making, I do want to talk about how do we even know if a decision is high stakes, right? This is not about what the most important person in the room thinks is a high stakes thing, right? It is about making architectural decisions around autonomy levels, the oversight, the accountability. And this is my personal framework on how I think about what stake this decision lies in. It includes elements of reversibility, exit availability, feedback latency, and I'm going to talk to this a little bit. I love to think about reversibility as one of the key axes here, which is, what are the chances that we can reverse the decision that is made? You were watching a movie on Netflix and you're done with it and you get another recommendation. Like, this is not quite for me. Worst thing that happens out of it is you go ahead, the machine learning model learns, and you're presented with a different option. Extremely low stakes, a really, really reversible decision. However, if you're talking about a pretrial detention, a wrong decision here is going to lead to a cost of jobs being lost, probably child custody lost, apartments lost. And this reversibility is what is really something that's going to make a primary axis of decision making. This is a really interesting case study. It's not an AI agent-based case study, but it's a real case study. So UK Post Office had deployed a software for accountants where they were trying to measure whether there were profit losses or if the numbers added up in every post office. And they noticed that for a large number of post offices, the accounts never added up. And so 900 postmasters were actually convicted wrongfully. And the cost of this was primarily driven by believing that what the software said was the right thing without actually taking feedback from what was happening on the ground. And even though this is not an agentic system, this is a design that we're going to see time and again where outcomes are made by systems where people have exceeding trust in it and believe that that's the golden truth. And this very much was irreversible. The other axis is thinking about exit availability. So did the affected person choose the system or were they placed in it? Can they get out of it if needed? The same thing, streaming recommendation, you can switch platforms. You don't like Netflix today, you move to Apple TV. That's your exit. You can choose to leave a system. But when you think about emergency room triage systems, the patient does not get an option to exit the system. They're subjected to the outcome of the model, of the designs that you have put in place. Amazon had a very interesting hiring algorithm. This was back in 2014, where anywhere there was women's written in someone's resume, women's chess, or sports teams, it used to penalize it. It was primarily trained on male-dominated data. Filtered applicants had no visibility that this was the reason why they were getting filtered. They did not opt into the system, but were subjected to the decisions made by a system, and there was no alternative process. The third axis is a very interesting one. It's interesting because it is not the most concrete to measure, which is the feedback latency, right? So with recommendation systems, you have a wrong feedback. You know in milliseconds when people just switch over to the next thing. When we think about agents in healthcare, it takes days to weeks for these outcomes to manifest and for you to know what's going on with the system. And when it comes to legal systems, it takes months to years to identify that there's an issue with the decision-making process, with the way the outcomes have been presented. I'm sure folks have heard about Zillow's iBuying collapse. This was a fun one. Machine learning models were sort of utilized to identify prices to buy homes that could be then placed for resale. The model was pretty good. There was a small error, but the feedback arrived months later, where Zillow had acquired a bunch of these homes at prices that became extremely hard to sell at. Because this feedback is so delayed, the house purchase followed by sale, these errors just keep accumulating. It's not that the model was bad. I want to repeat that. It's just that for that little use cases where the model was not accurate, the errors just keep accumulating. $500 million in write-down, and just because this feedback loop was really long. And so when we think about high-stakes decision-making, this is a catalog I like to build for ourselves. So if they're all three axes are high, you have to deploy strictest autonomy. This is where you need a lot of transparency, critical correction loops. If it's a mix, you have one dimension that is pretty high, the other two low. You have the option to design for fast feedback in some other dimensions, slow and thoughtful building for the one that is higher. And if all three are low, this is a fun use case to play with. You can have highly autonomous systems, lighter oversights, because the errors are recoverable. And so when you're thinking about it, on what sort of agents to deploy, because it's not just about one or the other. When you're building a system, there are multiple decisions to be made. And for each of these decisions, you want to catalog these decisions and identify where do they sit in the scale, and then use that to decide the autonomy to be granted for each of these agents, for each of the decisions in this large system that you're building. So that was a lot about just thinking about what is high-stakes decisions, right? I want to get into the core of the conversation, which is how to even design for these high-stakes systems. I want to talk about how we earn autonomy through stages. And I always tell teams, I always think about agents, that agents have to earn autonomy. We don't automatically grant it. And the reason why we have to earn autonomy is because of some of the things that we spoke before, right? The stages of this is, at the lowest level, you start with shadowing or suggestion modes, right? So very simple. Microsoft Word autocorrects are suggestions, right? It's observing your environment, it's providing autocorrects for you. It could be shadow agents where they're just watching what you're doing. That's your level 1 of autonomy you're looking at. In level 2, there's a lot more about confirmation. So the agent recommends, the human approves, there's a consequential step, the agent acts. So there's a suggestion, approval, action. And that's a really nice flow. The third level that we are looking at is about monitoring. So the agents are acting autonomously on most of the use cases, but the humans are frequently reviewing samples to see what sort of anomalies pop up. And some of the things that are to watch for are really critical here, because what you're watching for in level 1 is just what sort of clustering is happening in the way it's suggesting. At level 2, you're looking at how often is the human approving, not approving, the decisions that the agent is recommending. At level 3, you're not only looking for what is being overridden as part of the review, but also just the decision distribution shift, any systematic behavior changes. And then the last level is full autonomy. The system has earned it. It demonstrates reliably across the full distribution. For some of these decision types, it may never be appropriate, regardless of how accurate you've reached this stage. But this is a stage where we are seeing a lot of real-world things arriving into as well, right? Let's go through this. Something that I use often as a thought exercise on autonomy is this concept of asymmetric cost gate. On one side, you want to measure what the false positive rate is, right? Like, does the agent act when it shouldn't? And the cost of this actually falls on the individual that is subjected to the decision. So that's your false positive. But on the other side, you have the false negative. What happens if the agent does not act when it should? And the cost usually falls on the organization because more humans are in the loop. So you originally expected that the AI would take down the costs, but the agent is not even acting when it should be doing what it should do. and you're incurring these costs. And so there's this balance here. Very rarely it's going to be equal, right? Sometimes one side is going to weigh significantly higher than the other. And that's the constraint that we have to consistently think about, not just the accuracy. The model could be highly accurate, but the false positive rate, maybe say, is 6%, but the decision stake is extremely high. And that's when you're now choosing autonomy back again using the framework we spoke about. And this is, I think Waymo is a very interesting, it's controversial, but interesting, on how in an agentic world, it's earning autonomy in practice. It took them decades to be the autonomous systems they are right now. So they started back in the shadow mode where vehicles were in live traffic, safety drivers in the seat, and in that shadow mode, the system was prompting directions like next steps, and those were being mapped with what actions the driver was taking. So there's absolutely no harm here because you're just in a shadow mode totally. Then they started with limited pilots, right? So public roads with safety drivers present, but it was very, very scoped. Then they moved into geofenced, but driverless. So you have controlled environment, controlled geography, but there's no human in the loop. And this is closer to the level 3 that we were talking about. So humans are reviewing these samples, trying to see what's going wrong. And finally, you're at a stage where you're expanding geographies. Each level is earned by demonstrating reliability on the full distribution. And decades, this is decades of work. And so the stage deployment was not an issue because that was a feature, not a bug, right? The second principle that I love to think about when it comes to designing for high-stakes systems is transparency that demands engagement. And this is a little controversial, so stay with me. Everybody says you should have explainable AI. Make it as explainable as you can. Give us as much detail as you can, because that's what makes things more trustworthy, right? So there's a study done by Stanford that they had inserted placebic explanations. So there's no real information. The model's actual reasoning is sort of mimicked and is presented to the users. And the users still continue to trust it because it just sounds so plausible. None of it is real, but the perception of trust sort of amplifies just because you see it giving you these long reasoning. None of it is real. There's another study that was done by Nature magazine, and what this paper talked about was there was an AI glaucoma test detector, and when this AI was paired with the experts, the optometrist, human AI collaboration was fantastic. It was better than the human only. However, when this human was watching an AI with explanations, it was more likely to agree with AI even when the explanation was wrong, just because there was a sense of an explanation, versus a case where there was no explanation. In those cases, humans actually were critically questioning on because I don't know how you're reasoning, I'm questioning a lot more. I'm not saying that you should stop giving explanations, so TLDR, but it's a lot about anchoring and automation bias. Humans tend to really, really anchor to credible seeming outputs. And that confident posing explanations are not a real sign of trustworthiness in the system. It's just on our belief of how we trust them or the mechanisms by which we trust them. And so what I usually prefer is the engagement aspect of this, right? So let me move this here. Instead of just saying that this is a low risk or a high risk, something that really works well in production is a model is 61% confident, and these are the two competing hypotheses that is leading to that sort of number. And when you have an explanation that is not just low risk and convincing you of one option, but rather talking through two alternatives that the model is struggling with, you're likely to engage because you're seeing contradicting viewpoints. Friction on doubt and not friction on everything. Every system right now, especially in Copilot style, is, are you sure? Do you like this? So there's a prompt that comes after every action. And this leads to another of that automation bias examples where you're just so used to saying, yes, yes, this is good to go, this is good to go. And having friction at the right point in time or dynamic friction leads to highly accurate outcomes compared to this automatic yes, yes, yes. And so introducing this friction at the right points is the key here. And then the last one is exposing what the model does not know. A lot of our explanations are all about what the model knows. Most of the times when you read these natural language explanations, it's like, because of this, I've concluded. But it never really talks about what it doesn't know. Technically, it's not supposed to know what it doesn't know, but talking about variations in hypotheses or time changes. So let's say, for example, encouraging the model to reason that if you don't have last X hours of data for a medical patient, call that out. This is what my risk is, but I still don't have this data that I'm supposed to have to make this particular decision. And so this is something that I've really seen working really well in production. Principle thing, 3, evaluate the human agent system and not just the model. We are so used to traditional ways of evaluating models, which is you have a beautiful held out data and you do all the right things with the held out data set, but it tells you nothing about what happens when the model hits production. Not only just model hits production, but a human interacts with that model in a complex ecosystem. And so what really matters is a joint activity testing. So you're not just testing a model in isolation, you're testing a unified loop where there is an agent acting, a human acting, followed by an agent, followed by a human. This helps us observe some really interesting patterns, like when is the human really overriding the agent? What instances? It's possible that in offline state, the model was supposed to be super accurate, but in production, maybe it's overriding because the human is seeing an additional data point coming through. And those are interesting things. And often people feel like if I see a lot of errors in joint activity testing, the evals never worked. The truth is, if you see errors in joint activity testing, the way you're evaluating is actually working, because this is how you're going to know what your system's going to look like consistently with time with that human agent in the loop. Let's go to the left. This is my last principle, deploy for correction loop. And it's a real fun one. So we as humans, we adapt to agents, right? Every time you have an agent that can do something, that is mundane, that you're typically used to doing, you start collaborating in a way that you trust that agent. The human skills atrophy, because why would you keep up on a skill that the agent has already taken over and wasn't the most interesting thing anyway? However, the agent does need human correction for it to get better, for it to adapt to changing data. Because every overridden data point means that there's something wrong, right? It serves as a feedback loop. And so humans are getting comfortable working with AI. There is a sort of automation bias where we're just clicking through, all good, all good. But the model by itself is really reliant on the human making that correction. And this particular trap is the problem here. And this trap is going to become an even bigger problem, because when you actually need that sharp human judgment, you have systematically reduced the supply of that judgment. And so the way I think about an architecture to design for this correction loop involves a few points, so stay with me, is first around instrumenting every override. So it's not just about what the agent recommended, it's not about the confidence level, but also every action that the human chose. So in Microsoft Office, we used to track every click, any non-PII click, so that we know what was the recommendation, what did the human do, what was the recommendation, what did the human do. And this leads to your key data point that you will learn consistently on. You not only triage decisions as is as a whole, you actually divide them into high confidence, high stakes, low confidence, low stakes. What were the overrides for high confidence, high stake? Because if there was an override for a high confidence decision that was made, there's something systematically wrong with the model that's predicting something in a high stakes situation with really high confidence. Versus low confidence, low stakes is a completely different override. It could be a preference override. And so thinking about every decision type and how we triage it is super important in this full correction loop. You want to close the loop to training, right? I'm not saying you need to have RLHF, right, running all the time, but you can have a system where you collect this data systematically at regular intervals to retrain the model, to update the context, all versions of this. You want to monitor the behavioral drift, right? So you're not only tracking the AI agent's behavior, so you're obviously seeing what sort of decisions it's making, what's the distribution of these decisions, but you also want to track the human behavior drift, right? If at a point in time for a given model, X% of corrections or engagements were made, what is happening now? Why is there zero engagement? Is it because the model is perfect? Or is it because that the humans have just gotten used to the model? And then the last one is around watching escalation rates. So if the agent stops escalating things to the human in the loop, right, bringing in the human at the right point in time, it's interesting to see what's going on with the data that's leading to that behavior. Any sort of spikes means the input distribution is changed. And so this correction loop architecture has been super valuable every time we've thought about bringing these systems into production, thinking about how do we design that human-AI collaboration and monitor that human-AI collaboration systematically. Let's go. We're back to the hospital. And it was a long ride, I know. We had 10 ICU beds, 40 patients, and decisions that we need to make every hour. And so when I first posed this question, the question was, what do we need to see so that we can actually reliably deploy this in real life? And what we need to see is how has the system earned autonomy? So you'd probably start at level 2 maximum, where you have some sort of a recommendation, but the human in the loop is correcting it. And maybe system earns itself to level 3 in a shadow mode, right? It consistently works towards getting to some level of autonomy. We think about demand engagement. So agent surfaces what it knows, what it doesn't, and makes its own limits visible. And so when it's talking about predictions, it's not just low risk and why, and what are the alternating hypotheses that are debated with as well. We're evaluating jointly. So we're not only evaluating just the model, 99% on holdout set. We're really thinking about how the model and the human are going to work in production. And do the coordinators, the human in the loop, engage more, or do they engage less with the AI with the time given? And the correction loop, right? Every override that is captured by type, confidence, it's very possible that the clinician is overriding an AI prediction because it knows that the family is coming through. You know, they know that there's an external data point that's presented to it that the model probably didn't. You capture that. You inform the model that this is another data point to look out for. And that's the correction loop we're talking about. All right. Here's what I'm going to leave you with. With AI agents, we're not just building software. Software automates tasks, right? What we're doing is redesigning how decisions get made, who has the agency, what information shape the outcome, and where the accountability lives. These decisions do matter, and they matter a lot, most in healthcare, in criminal justice systems, in legal systems, financial systems, education, which are often low resource, have a lot of constraints, financial as well as in terms of human resources. And more than anything, it's slow and inconsistent. With AI agents that are built well, we can make these systems fast, we can make these systems consistent, and with better information, we could really reimagine how these systems are being made. And for this case, the technology is not the hype, right? It's very, very real. It's real in a way where we know we have agents that can plan, that can make decisions, that can execute in environments. And so the question is not about whether we build them. It's whether we build them in a way that elevates the human judgment. It's whether we build in a way that humans are truly in a loop and not just for the heck of it. And lastly, whether these decisions allow us to come on the side where the outcomes are meaningfully better and the outcomes are meaningfully something we can stand behind. And so let's design them well. Thank you.